everyone, let's look at another trig substitution. This time let's look at a definite integral. I'm not going to do a ton of these, but I want to make sure I do at least one definite integral so that you get the idea, kind of the same idea as it has been for W substitution. Okay, so looking at this one, first thing I see is I've got that sum of squares showing up again, and I know from the last example that a good way to eliminate that is to use a tangent. I have to be careful though, because what I want is 1 plus tangent squared theta, and if I just use tangent, I'll get 36 plus tangent squared theta. So I need to throw an extra 6 out in front so that once that gets squared, I have a 36 that I can factor out. Do not forget to figure out your dx. So the derivative of tangent is a secant squared, so that's going to show up as well. So what I've got right now is x squared, so 36 tangent squared theta over 36 plus 36 tangent squared theta times 6 secant squared theta d theta. Oh, hold on, I just assumed that was there, but I see a typo. There should be a dx there, or something really weird is happening. So the dx got replaced with the 6 secant squared theta d theta. Okay, so I want to be a little careful now. I have a definite integral, so I want to be careful about writing 0 to pi over 4 is definitely not what I was thinking. This one has all sorts of typos. Pretend I didn't say that. I know that's where I want to end up. Here, we'll just keep it in blue. But I'm pretty confident this originally said 0 to 6. Okay, so here's the deal. If we want to put in limits of integration on this new integral, they need to be theta values. So I need to go back to this x equals tangent theta. Whoa. And I need to say, okay, well, if x is 6, I'm going to start with the 0 actually. If x is 0, what is theta? And the answer is we can divide by 6. We get tangent theta has to equal 0, which has infinitely many solutions, but as we work our way through this, we're going to be using inverse trig. It's going to restrict us to just the stuff really close to theta equals 0. So I think what we're looking for here is that tangent equals 0 when theta equals 0. So that's not terribly exciting. When x is 0, theta is also 0. When x is 6, I'm going to work my way back through this. I can divide out the 6. I get tangent theta is equal to 1. If I take the inverse tangent of 1, so I'm trying to figure out when tangent equals 1, which means slope is 1, I'm right smack in the middle of quadrant 1, which means that I want my theta to be pi over 4. Okay, again, you do have the option of just switching back to x's when you get done with this, and that would be fine. If you're going to do that, then anytime you write 0 and 6 as limits of integration, you have to write x equals so that I can see that you know those are not actually theta values. Okay, so tiny bit of scratch work on this one. Again, if you get to the point where you don't have to write this out, excellent. What would happen here is we'd factor out the 36. We'd get a 1 plus tangent squared. If you don't know your Pythagorean identities, memorize those two that I have at the beginning of the packet. You'll need them. 1 plus tangent squared theta is secant squared theta. So this is going to turn into the integral from 0 to pi over 4 of 36 tangent squared theta over 36 secant squared theta times 6 secant squared theta d theta. Looks like 36's are going to cancel out for me, so that's nice. It also looks like secant squared is going to cancel out for me. So I'm going to be left with a 6 times the integral from 0 to pi over 4 of tangent squared theta d theta. There's a couple ways to deal with the tangent squared theta. So one of them is to write it as sine squared over cosine squared And then you'll have to use Pythagorean identity to say sine squared is the same as 1 minus cosine squared, and you could split them back up. That's actually the long way, though. I just find that people do it, and sometimes I catch myself doing it, because if it's tangent, like the last problem, that's exactly the method. But here, there's actually a quicker way. Remember, the Pythagorean identity that we just used said that 1 plus tangent squared is equal to secant squared, which we could rearrange and say, well, then tangent squared is the same as secant squared theta minus 1. And we actually know that the antiderivative of secant squared is tangent, and the antiderivative of 1 is theta. And then since we have changed our limits of integration to be thetas, we don't actually have to draw triangles and switch back to x's, although in this case it's pretty easy to switch back to x's. Sometimes that's easier than others. But we can just go straight to plugging in. So we get 6 tangent theta. Tangent of pi over 4 is 1, plus 6 theta. Theta is pi over 4. And then we want to do the same thing but plugging in 0, which actually looks like it's going to be not that exciting. Tangent of 0 is 0, and theta equals 0 gives us 0, so it's really just this. So I'm going to say I have 6 plus 3 pi over 2. Okay, so definite integrals, it's nothing too crazy, but if you switch your limits of integration, it's a little funny because you actually have to plug in the value, the x value on the on the right hand side and solve for it. Shouldn't be too messy to solve, but it is a little different. Thanks for watching.